Hello everyone and welcome back to another video. Sorry for not uploading much lately. School's been pretty busy, so I haven't been able to get to uploading. But today we're back with another video, and we're just going to be doing one problem from the European Physics Olympiad, and it's the 2018 European Physics Olympiad problem 1, and it's called 3 balls. And let's just get right into it. 3 small identical balls, denoted as A, B, and C, mass M are each are connected with 2 massless rods of length L, so that one of the rods connects the balls A and B, and the other rod connects the balls B and C. The connection at the ball B is hinged, and the angle between the rods can change effortlessly. The system rests in weightlessness, so that all the balls lie on one line. The ball A is given instantaneously a velocity perpendicular to the balls. Find the minimal distance d between the balls A and C during the subsequent motion of the system. Any friction is to be neglected. Alright, so let's just draw out the situation here first. So we have 3 balls and the third one there, and they're labeled A, and they're labeled A, B, and C, and each of them are connected with massless rods, and these are length L, and all of these masses have mass M. And initially the ball A is given instantaneously a velocity perpendicular to the rods. Let's say it's given some velocity v. And so after it's given velocity v, let's think about what happens. Well, it's going to start rotating, and then that's going to mean the other things are going to have to move to account for conservation of momentum, and and that's also going to change some angular speeds, and that's going to cause other things to change because of conservation of angular momentum, and there's going to be all this complicated motion going on. But the problem really only asks us to find the minimal distance d here. So that's some state farther along in the motion, right? And that means we kind of can ignore the actual motion. And the way we do that is by utilizing conservation laws. And let's think about what's conserved in this system here. Well, we have that the rods can change effortlessly. That essentially means that it's frictionless. So let me write out conserved quantities, and I'll list them here. So first one we have from that frictionless thing is conservation of energy. And now from the second part, sorry, not from the second part, but there's no other external forces acting on it, so we have conservation of angular momentum. Sorry, not angular momentum, conservation of linear momentum. And lastly, we can conserve angular momentum because there's no external torques. And one other special thing here we can do is we'll conserve about center of mass, since that's allowed. And you can check out any mechanics textbook for that. So all that's left here is we need to figure out what the final state of the system is going to be at minimum distance d, so we can somehow relate all the equations that we can get out of this and find the actual distance d. And I think this part is probably the best part of this problem. Once you realize this, it's it's very fun to solve once you realize this. And well, I guess that's the best part of the problem. And so I think it's worthwhile to do it on your own. So I'm gonna let you guys pause the video and figure it out. And as a hint, consider the classic problem where you have two boxes connected by a spring, and the initial one given some velocity v0, v0, I don't know, and finding the minimum distance. And finding the minimum distance is when the state is like this, with both boxes moving at v. And try to figure out why this is, and try to apply this to the situation here, and you should be able to figure out, or not you should, but you might be able to figure out what the final state is. Alright, welcome back if you paused the video, and if you didn't, I guess you just heard an awkward pause. So the final state is going to be where all three masses are situated as shown, length L, L, and D, and it's going to be a rigid body rotating at some amount omega, and the center of mass moving at some velocity v. I guess I'll attach a subscript or actually I'll give this a subscript v naught and make this v to make it easier. And the reason for this, well, the center of mass moving at some velocity is not really relevant to this because that's just going to be true either way. The reason that it is a rigid body, meaning that the angle here is not changing. And the angle here not changing is just going to be the reasoning behind why it's a rigid body. Because if the angle was changing, let's say theta dot is greater than 0, then some time before the current snapshot here, then the masses would be closer together, because theta dot is decreasing once you go backwards in time. And if theta dot is less than 0, then obviously going forwards in time, you'll have a smaller angle again. So we must have that the angle is not changing, and so it's a rigid body. So all we have left to do is apply all of these equations, since we know what the state here is, and we can find the moment of inertia here, we can find the velocity, and we can find angular momentum. So all that's left here is to find all of these and equate them to the initial state. So first let's start with the easiest one, let's say conservation of momentum. So we have the initial momentum here is mv0 is going to be equal to 3m times the velocity of the center of mass, which is just denoted v here. And that's equal to, and so that implies that v is equal to v naught over 3. And so that's the conservation of momentum there. And now let's apply conservation of angular momentum. And this is going to be about the center of mass. So in the initial setup here, the center of mass is right here by symmetry. And so the initial angular momentum is going to be mv0L, just by its definition. And the final angular momentum here, since it's going to be a rigid body, is going to be the moment of inertia times the angular velocity. So it's going to be equal to I omega. So we need to find I. And so, well, this can be rewritten as omega is equal to mv0L over I. So now we have the velocity and the angular acceleration, so we can apply conservation of energy, which is the last one left, by setting the initial energy equal to 1/2 mv squared plus 1/2 I omega squared. So now applying energy, 1/2 mv naught squared, which is the initial energy, is equal to 1/2 times 3m times v squared, which is v naught over 3 squared, plus 1/2 I omega squared. And now we can substitute both of these in, well, we already substituted one of them in, and that equates to 1/2 m times v0 squared over 3 plus 1/2 times m squared v0 squared L squared over I. So we can cancel some things here. Let's cancel all the 1/2s, and let's cancel the v0 squares. And let's cancel m's. So what we're left here is 1 is equal to 1/3 plus ml squared over I, and that gives I is equal to, so this is going to be moving over its 2/3, so and then multiplying over it's 3 halves, and multiplying over the I. So I is equal to 3 halves ml squared. And this is going to be I about the center of mass, since, well, that's how we consider energy normally. And so let me bring this diagram over below, or redraw it. So all we're left is computing this I center of mass. So we have the setup here with 3 masses. This length is D, L, L, and M, M, and M. So we have 3 point masses, which means we can compute the center of mass location by considering the centroid, which is the intersection of the medians, and actually only draw the middle, the central one, so that the diagram isn't cluttered. But you can see that it's going to be the median because it has to be in between, and it's going to be weighted more heavily on this side than on that side because of the 2m. So it's going to be 1/3 of the 1 to 2 here, which is just the centroid. And so we just need to find these 3 lengths, and we can find the center, the moment of inertia. So first, by Pythagoras Theorem, we have the total height. So let me label these masses A, B, C, and I'll call this point D. So we have the length BD is equal to the square root of L squared minus D over 2 squared. And we also have the length, well, so from there we have the length, I'll call this G, BG is equal to 2/3 BD, which I'm not going to rewrite. And lastly, AG, which is equal to CG by symmetry, is equal to the square root of GD squared plus AD squared, and GD is just equal to 1/3 of BD, and that's squared. For simplicity, so I don't have to write D over 2 over and over again, I'm going to let X equal to D over 2. And so now we have the moment of inertia is equal to M times, so BG squared is going to be the first one, which is 4/9 times L squared minus X squared plus, well, now we want 2 times AG squared, and so we write AG squared, which is equal to GD squared plus AD squared, which is equal to X squared. And we know GD, let me just write it here, GD is equal to 1/3 of BD. So we can rewrite this part as 1/9 times L squared minus X squared. And we know that this is equal to the I center of mass, which here we found was 3 halves ml squared. And so let's write that in here. And we can cancel the m's. Oops. We can cancel the m's first of all. And now let's just write out everything here. So we have 4/9 L squared here, and we have 2/9 L squared here. So that's going to add up to 2/3 L squared. And we have we have 4/9, negative 4/9 X squared here, minus 2/9 X squared here, and then plus 2x squared here. So that's 2 minus 2/3, which is equal to 4/3 X squared is equal to 3 halves L squared. And we have, so 3 halves is equal to 9 over 6, and 2/3 is equal to 4 over 6. So we have 4/3 X squared is equal to 5 over 6 L squared, which means that X squared is equal to 5/8 L squared, which means X is equal to 1/2 times 5 over 2 L. And the last thing here we need is x equals, well, I guess it's slightly cut off here, but x is equal to d over 2. So then the half is going to cancel. So d is equal to root 5 over 2 L. Alright, so that's the end of the problem, and I hope you guys enjoyed it. And it only took this much math, and that was just geometry, pretty simple geometry. And the main part of this problem here is realizing that this here is the final state, and this is what I think makes the problem really fun, and it's really elegant because it feels like you might have to get like some velocity dependence, but in the end all you get is this simple relation, d is equal to root 5 over 2 L, which I guess is correct by dimensional analysis. So I hope you enjoyed the video, and thanks for watching.